Okay, welcome back, and today we're going to cover section 8.3 in chapter 8, and we're going to talk about probability applications of the counting principle. So now what we're going to do is we're going to take everything that we've learned from the last two sections, and we're going to apply it to the idea of probability and in application type problems. So the first thing we're going to do is do an example. Okay, so now in this example, we have the EPA is considering inspecting 6 plants for environmental compliance, 3 in Chicago, 2 in Los Angeles, and 1 in New York. Due to the lack of inspectors, they decide to inspect 2 plants selected at random, one this month and one next month, with each plant equally likely to be selected, but no plant is selected twice. Okay, so what is the probability that one Chicago plant and one Los Angeles plant is selected? So one way of doing this is setting up a tree diagram. Okay, so if we look at the first month, okay, so the first month we have, we're going to choose a plant. And so if we look at this, so the first month we're going to choose a plant. And so we have Chicago, LA, and New York. Okay, so what's the probability of choosing these 3? Well, they give us the information that there are 3 plants in Chicago, 1 in New York, and 2 plants or hold on, there are 6 plants. So there are 6 plants, 3 in Chicago, 2 in Los Angeles, 1 in New York. Okay, so that means out of the 6, there's a 3/6 chance, or 1/2, that the plant is going to be from Chicago. 2 out of 6, or 1/3, LA, and 1/6 New York. Okay. Now the second month. Now again, we can only choose the second plant for the second month is going to be based on the fact that we can only choose cannot be selected twice. Okay. So what we're going to do then is pick out the probabilities of these. So here's Chicago. So now notice on the second month, notice that what do we have here? Well, the probability is going to be changing. Okay, so you can only choose one and it can't be selected twice. So what's going to happen here? Okay, well, to set up our tree diagram, we start looking at the probabilities for each event. Okay, so in here we have these. So the first month it's going to be out of 6, right? Now, on the second month, well, we've already chosen one of the 6 plants on the first month, and right, and since we can't choose the plant again, then there's only going to be 5 remaining for the second month. Now, so think about this. If we chose Chicago the first month, then the probability of choosing Chicago, one of the other 2 plants from Chicago, is going to be 2 because we're down by 1, right? So it'd be 2 out of 5. LA is going to stay the same. It's going to be 2 out of 5 though instead of 6, and then 1 out of 5. Okay, and so this is conditional probability, right? So these are all of the conditional probabilities based on the fact that the first plant came from Chicago. And then likewise, we're going to do the same thing for LA. Notice that again, all of the plants are now 5. There are only 5 available. And now this time Chicago is 3 because Chicago wasn't chosen the first time. LA was. So now we still have 3 Chicago plants to choose from out of 5. But now we only have 1 LA plant because, again, no repeats. Okay, so we have 1 out of 5 here, and then of course 1 out of 5 here from New York. And then similarly for New York, now it's going to be 0 out of 5 because if we chose the only one for New York, that means that there's 0 left for the second month, for the second choice. And so then there's 2 out of 5 here and 3 out of 5 here. And now we've got our tree diagram completely set up. And so if we wanted to know what is the probability that one plant is chosen from Chicago and one plant is chosen from LA, well, Where can we do? Well, LA could be the first one, and Chicago could be the second one, or Chicago could be the first one, and LA could be the second one. And so we have to take both of those outcomes together. And so we're going to multiply down the branch, right? So we use the multiplication rule for conditional probability, right? So the multiplication rule, these are dependent events, right? So this is going to be 3/6 times 2/5, which gives us that one, or 2/6 times 3/5, which gives us this one, and then we're going to add them up. Okay, so what do we get? Well, we get the same thing. We get 6/30ths, or 12/30ths, or 6/15ths, which is going to be 2/5, which is 0.6, or excuse me, 0.4. No, it's not. Yeah, it's 0.4. So the ending probability is going to be 0.4. Okay, so here's the idea. Okay, so we find the probabilities, and so these are going to be combinations, right? Because we don't care about the order, right? Order doesn't matter here. So we can also use combinations here. And we say, okay, well, how many different combinations can we have for this? Okay, so what is the probability that one New York and one Chicago plant is picked? Okay, well, in this case here, we're going to go down what? Chicago, anything that gives us both Chicago and New York. And so we get this, right? So we go down Chicago and New York, which is 3/6 times 1/5. And we go down New York and then Chicago, which gives us the same thing, 1/6 times 3/5. And we get 2 times 6/30ths, which gives us 1/5. Okay, in this case. Okay, but we could also have done this with combinations easily. So if we look at this, we could have done set up our probability this way. So let's do it this way. So we could have set up our probability of what is it, New York and Chicago. So now, how many different ways can we choose both New York and Chicago? Well, how many different ways can we choose both New York and Chicago? Well, how many Chicago plants are there? Well, there's 3. How many New York? There's 1. Okay, so we want to choose 2, 1 from each. So we want to go, okay, we want to choose of the 3 Chicago, right? Of the 3, we want to go choose 1, right? And then of the 1 New York, there's going to be, we're going to choose 1, right? And then the multiplication principle says, let's multiply these together. So this is going to be the total ways of getting 1 from Chicago and 1 from New York. And so what is this? This is going to be 3, and this is going to be 1. Okay. So now we know the top number is going to be 3. Okay. Now, what about the total number of possible outcomes? Okay. The total number of possible outcomes of choosing 2 out of the 6 is going to be what? It's going to be 6 choose 2. Okay, and so how do we get that? We're going to do the calculator. So let's see what that is. Okay, let's see. We'll have, oh, come on now. Okay, so we're going to choose 6, or out of 6, and we're going to choose 2. And we get 15. So the answer is 3 out of 15, or 1/5, which is the same answer as we got before. So we can use the definition of probability and use what we know about combinations, because all order doesn't matter in this case. So remember, notice that this one, so we're choosing 1 from the 3, so we're saying, okay, one of the 2 positions that we're choosing has to be from Chicago, and the other one has to be from New York. Now we could also, remember what I said, we could add the LA one, but we're not choosing 0 from LA. We're choosing 0 from LA, which means of the 2, we are choosing 0. So we know that this is going to be 1. And so we get the same answer. But notice that this number plus this number plus this number adds up to the bottom number here. And 2 plus 1 plus 3 adds up to the 6. That should always be the case. Okay, but again, once you get used to knowing what you're doing, then it'll just be this. So this is just using the definition of probability in combinations, where this is using the tree diagram. And again, depends on how many branches you are, but this can get tedious. Let's say if we were choosing 3 branches over 3 months. Let's say we're doing, let's say we had 12 let's say we had 4 locations. We want to choose 3. Let's say we had 4 locations and we had a total of 15 plants, and we want to choose 3 over a 3-month period, 1 each month. Okay, well, this would definitely make this get a little messier. Okay. Now, from a group of 22 nurses, if 8 of the 22 nurses are men, what is the probability that exactly 2 men are among the 4 nurses selected? So we're going to select 4 nurses, and we want to know, hey, we want to know what's the probability of exactly 2 men. Well, let's use our what we know. So we say the probability. So we're going to do the probability of what? Exactly 2 men. Okay. Well, order does not matter in this case. All we care about is whether there are exactly 2 men in the 4 people selected at the end. So now what we're going to do is, this is going to involve combinations. So we need to choose how many men? 4. And 2 of those, or excuse me, we need to choose 4 nurses, and 2 of them have to be men, which means of the 8, of the 22 nurses, 8 are men. So of the 8 men, we have to choose 2 of those. So 2 of the 4 have to be men. So let's say we're going to, how many different ways can we choose 2 out of 8? Okay, now we still have 2 positions left over. Well, those are going to have to be women, right? So then how many women are there in there? Well, out of the 22, there's going to be 14 women. So 14 have to be the other women. Okay, so 14, choose 2. And then, of course, we have to divide by the total possible number of ways that we could choose 4 nurses out of what? 22 nurses. So the bottom would be 22, choose 4. Okay, so now notice that 2 plus 2 equals 4, and 8 and 14 make 22. So now all we have to do is plug and chug. We've got the total number of ways of choosing exactly 2 men out of 4, and we got the total number of possible ways of choosing 4 people out of 22. And so all we have to do is put this in our calculator, and we're done. So let's see. So we're going to do 8, choose 2, which is 28. Okay, and then 14, choose 2 is 91. And now 22, choose 4 is 7315, 7,315. Okay, and when you plug it into your calculator, what do we get? Well, we get 28 times 91 divided by 7315. And we get 0.348. 0.348. Okay, and that is the answer. Okay, so we get 0.348 as the answer. And notice that's exactly what we got. Okay, so we got 7315 for the total. Notice that 22, choose that, and we got 8, choose 2 times 14, choose 2, which is this, which is 2448, and we use the definition of probability, and we get 0.348, and we're done. Okay, now let's go on. Let's see here where we're at. I just want to make sure. Let's see, that one. Okay, so let's do this one. It says, when shipping diesel engines abroad, it is common to pack 12 engines in one container. Suppose that a company has received complaints from its customers that many of the engines arrive in non-working condition. To help solve this problem, the company decides to make a spot check of containers after loading. The company will test 3 engines from a container at random. If any of the 3 are non-working, the container will not be shipped until each engine in it is checked. Suppose a given container has 4 non-working engines. Find the probability that the container will not be shipped. Okay, so in this case here, so we have how many engines in the container? We have 12. Okay, we're going to select 3 engines at random out of the 12. Okay, we know that 4 of the 12 engines are not working. Okay, now if any of the 3 engines, so meaning if at least one of the 3 engines are not working, then the container will not be shipped. Okay, so that's what we need to find. What is the probability that the container will not be shipped? In other words, what's the probability that at least one of the 3 chosen container or chosen engines will not be working? Okay, that's the idea. Now, does order matter in this case? Okay. The answer is no. Order doesn't matter. Okay. And again, I'm assuming that they're choosing the three engines at random, and then they're going to test all three engines. Okay. So that's going to be the setup. So we're going to be dealing with combinations. Now, in this case, because we're dealing with at least one, the easiest way to do this is to use the complement rule. Okay, so why is this? Well, let's back up. Okay, so if I want at least one, so we want the probability that at least one of the three. So the number of defects we want to know is at least one. Oops, hold on. Okay, so we want x to be greater than or equal to 1. Okay, so if we were going to do this, we would have to figure out what? We'd have to find the probability that of having exactly one defect, right? One defective out of the three, plus then we'd have to find the probability of having two defective engines, and then we'd have to add the probability of having three. Okay, so we'd have to do three calculations, and so we'd have to find the combinations for this plus this, and we'd have to add up all three of these probabilities. But if we use at least one, well, what's at least one mean? It means 1, 2, 3, or more, right? But what's the opposite of that? What's the complement to that? Well, that means you could either have one or more, or you could have zero. And so we could use the complement rule and say, okay, well, the probability of at least one, right, is equal to 1 minus the probability of 0. Okay, so now we have this probability. So again, well, you could have one or more or none. So anytime you have at least one, and they were asking for at least one, always use the complement rule. Because remember, if you have two complements, like yes or no, on or off, then what's going to happen? The probabilities, those probabilities have to add up to 1. So this probability plus this probability has to add up to 1. And so that's why we can use this to our advantage. And now we can say, okay, we want to use 1 minus the probability that there are 0 defective engines in our sample of 3. So that means, well, of the 4 defective engines, we're going to choose 0. And of the 8 non-defective engines, we're going to choose 3. So what's this one? This is going to be 1. And then 8 choose 3 is 56. And then we do 1 times 56. Notice 3 plus 0 equals 3. And 4 plus 8 equals 12. And then this combination is 22, or 220. And so if we do 1 minus this, we get 164 over 220, and we get 0.7451. Okay. Now we could have also calculated this, which would have been 0.2545, and then subtract from 1. That's fine. Either way, it doesn't matter. I probably would have just done that. Okay, so now let's look at this one. So in this case here, what do we got? We have, let's see here. Okay, so let's say we have birthdays. Okay, like for example, I've had a professor do this in our class for probability. One time is that we had a class of like 25 students in the class, and we talked about, hey, what's the probability that any two of the students in that class would have the same birthday? And the probability is actually quite high, higher than we thought. So in fact, if you see here, 25, the probability is quite high to have two people in the classroom to have the same birthday. Okay, so but how do we arrive at that? Now, so suppose that we have a group of n people in a room, and we want to find the probability that at least two of the people have the same birthday. So what does it mean to have the same birthday? It refers to the month and day, right? So not necessarily the same year. Okay, so we don't care about the year. We just care about people who have the same month and day as far as birthdays go. So we're also going to ignore leap year for the moment. Okay, so we're not going to consider leap year. And so we're going to assume that each day of the year is equally likely. And we're going to basically look at each case. And we're going to look at the case of n equal to 5. And we're going to find the probability that that no two people from among the 5 people have the same birthday. Okay, so notice how we're doing this. We're going to start with saying, hey, let's figure out the probability that no two people in the 5 people had the same birthday. So there's 365 different birthdays possible, and for the first of the 5 people, right? So the first person we're going to look at, right? So they have 365 days for their birthday. Okay, and then for the second person, well, they have 364 days to choose from, right? And then the third person, well, then they have 363 days for their birthday, and so on and so forth. So notice that, hey, once a position, so this is a permutation, right? This is a permutation because order matters, right? The first person has a birthday, and we're saying then the second person has the birthday, but it can't match the first person's birthday. So once we choose a date for the first person, then the second person can't have that date. And so this becomes a permutation type problem, okay? Okay, so now, how many different ways, okay, so let's see. So the number of ways 5 people can have different birthdays is going to be 365 times 364 times 363, 362, and 361. Okay, now, if we allow for repeats, right? So now we're allowing for any day, right? So now we're going to say, hey, how many ways possible are there for people to have either the same birthday or different birthdays? So in other words, how many possible permutations of birthdays can we have if we allow for repeated birthdays? Okay, now it's going to be 365 to the 5th power, right? It's going to be 365 times 365 all the way to 365 times, right? Because each person has 365 days to choose from for the birthday. Okay, possible. So the bottom number is going to be the total number of possible birthdays for all 5 if we allow for either same birthdays or different birthdays together. And so that's going to be 365 to the 5th power. Where the numerator, which is we're only interested in each person having a different birthday. Okay, now, if we calculate the probability that no two people have the same birthday, then we can use the complement rule to get our answer. Because if we first figure out how many different ways can we have different birthdays for every person, then the complement to that is having at least two people having the same birthday. And that's what we're looking for. So now, so for the first one, okay, so the first one, the probability, so the probability of 5 people having having different birthdays, right? So we're talking about 5 people. Okay. So 5 different. Okay, so 5 different birthdays. What do we got? Well, we end up with the 365, right? Times 364. I'm not going to write it all out, but 365 times so now all the way to so this is what we're doing, and so the probability turns out to be 0.9729. Okay, so this is the probability of having 5 people have different birthdays. And so the probability of having 2 people have the same birthday, so no 2 people having the same birthday, the probability of having 2 people have the same birthday is going to be 0.0271. And though, so you could do the same thing for each one of these. If you put 10, well, then now it's going to be what? 365, 364, all the way down till you get done with 10 people divided by 365 to the fifth. And so you could easily fill out this table by using the complement rule, because all you're going to do is, as you increase the number of people, this probability is going to go down, and this probability then has to go up all the way up to 1, where obviously 366 is, obviously you're going to have a 100% chance because there's only 365 days that we're using. Okay, so that's one way of filling out a table and using permutations or using combinations to help solve problems. Okay, so now, in this case here, what we're looking at is a probability distribution. Okay, so notice that if we take those numbers, right, and we take all of these different probabilities, notice that we're getting an increasing curve, and this is what we call cumulative probability. So it's cumulative because it starts at 0 and it's cumulative. And notice it has sort of like an elongated S curve. Okay, so notice that. Okay, so this is an example of how we can depict and show using a graphing calculator, showing the probability formula in this example. Okay, so this shows what? This shows the graph of the probability function. Okay, and so we can do the calculations for this by using this graph. We could actually graph it out. And so let's see here. And so we're going to do it at the integer points. Okay, so you can use a TI-84 plus C, and you can basically, you can solve the function and you can graph it by taking y equals 1 minus 365, and then you use your PNR, your NPR function, and then you choose, and then you have your R value just be x, and then you divide by 365 raised to the x power. And if you stick that in your calculator, and you want to go from 0 to 44, let's say, and you can plot this on your calculator. Okay, but again, just a way of graphing this on your calculator. And I'll show you this, how to do this in class as well, and we can do an example. But again, this is just a graphical display of how you can show a probability function, in this case, cumulative probability. So as probability changes, as the n increases. So here they went from n equals 0 to 44. So obviously at 0, the probability is going to be 0, and at 44, it's going to be 1. And then these are all of the individual probabilities from basically 0 to 44. Okay. Okay, so now next time we're going to talk about a special probability distribution called the binomial distribution, binomial probability. And so along with this makes calculating probabilities a lot easier because we're going to introduce a formula, but also it makes things quick and easy because once you know a distribution, one of the things about statistics and probability is that if you know about the distribution of a population, for example, if it has a binomial distribution, like in this case, we're going to be able to calculate things very quickly and more easily than using the definitions of probability and combinations and permutations that we've been using. So until then, please make sure you go through the examples. There are other examples and try-its in the textbook. Do those for practice. And when we come to class, we're going to practice this stuff. And again, make sure you write down your questions. Make sure you practice. And if you get stuck on something, ask in class. And start working on the homework. And if you get stuck on the homework, ask. That's what the class time is going to be for. Until then, have a great day. Bye-bye.